Okay, so welcome to the AFMS seminar. So it's my pleasure to introduce Professor Pinaki Chakraborty from OIST, which stands for the Okinawa Institute for Science and Technology. So he received his PhD in 2006 from the University of Illinois at Ullmarch-Champaign. He was first at the Department of Theoretical and Applied Mechanics, but then moved to the Department of Geology to further develop his research career. In 2012, I think it's just after the OIST was founded, he joined there to lead the fluid mechanics unit. He's an all-rounder fluid dynamicist, using a nice combination of theory, experiments, and simulations on various topics such as geophysical, geological, atmospheric, and granular flows, etc. So the title of his talk today is the spectral link in turbulent frictional drag. So over to you, Pinaki.
Well, thank you very much, Kengo, for the kind introduction and also for kindly inviting me to present this seminar. And thank you everybody for attending this seminar. Okay, so I'm going to talk about this area we call the spectral link. And this has been an area I've been working on for about 15 years or so. And I'll describe some of the problems that we have worked on over the years in this area of spectral link. My close collaborator on every aspect that I'll describe today has been my colleague at OIST, Gustavo Joya. And over the years, we have been very lucky to have several collaborators who have contributed to various parts of this work. I would like to particularly mention Nigel Goldenfeld, Walter Goldberg, and Hamid Kelly. So for today's talk, the aspect of spectral link that I'll focus on is frictional drag, turbulent frictional drag. And by means of introducing why one would care about frictional drag, let me just pick two examples. So the first example I'll pick is from nature. So here's a satellite image of a tropical cyclone. A tropical cyclone is, of course, an extremely turbulent flow. And this turbulent flow experiences a lot of friction with the ocean underneath. And this parameter, the turbulent friction between the tropical cyclone and the ocean, is a crucial parameter that determines the intensity of the tropical cyclone. So that's an example from nature. And as a second example, I'll pick an example from engineering. So these are industrial pipelines, be they gas pipelines, oil pipelines, you name it. So the flow inside these pipes generally are turbulent, and this flow again experiences turbulent friction against the wall, from the inside of the wall that confines the flow. And it is this turbulent friction that sets the pumping cost of the flow. And therefore, if we can somehow reduce the turbulent friction, that translates into immense savings because these pipelines are very, very long. Okay, so that I hope kind of sets the stage for why one would care about understanding and predicting turbulent friction. And for the next part of the talk, I'll basically focus on flow inside a pipe. So let's consider a pipe of radius capital R, and we have a mean flow taking place from left to right, and the mean flow is of capital V. A velocity of the mean flow is capital V. Pipes are generally rough, but I'm going to focus on a very special kind of a rough pipe. This rough pipe has a single length scale roughness. So to arrive at a single length scale roughness pipe, we start with a smooth pipe of radius capital R. And onto the inside surface of the smooth pipe, we paste spheres, particles, grains of single length scale small r. So because of this activity, we have now turned the interface between the flow and the pipe to be a rough interface, and the length scale of this rough interface is small r. This turbulent flow with this interface experiences friction or shear stress, tau, that opposes the flow. And this is the tau that we are most interested in this talk. So the different dimensionless groups that characterize the problem are the dimensionless velocity, which is the Reynolds number, where nu is the kinematic viscosity of the fluid. There's a dimensionless geometric parameter, which is the size of the roughness to the size of the pipe, small r over capital R. I'll simply refer to this as roughness. And finally, the dimensionless shear stress, which in engineering literature is generally called friction factor. So that's my small f. And the problem that we are interested in is how does the small f friction depend on the Reynolds number and the roughness? So the classical experiments, and till date, the most comprehensive experiments that show this dependence, how the friction depends on Reynolds number and on roughness, go back to the experiments done by Nikuradze in Ludwig Prandel's lab in 1933. So I'll show this famous data from Nikuradze. So I'm plotting his data in a log-log plot, log of friction against log of Reynolds number. Nikoradze took 6 different pipes. He started with smooth pipes, and then he sieved sand grains so that they are of uniform size. And then picking different combinations of pipe radii and sand grain roughness, he pasted the sand grain roughness onto the interior of the pipe. So the inner surface of the pipe is made rough with a single length scale roughness. And he studied the flow of water flowing through these rough pipes, and he looked at 6 different roughnesses. Okay, so when the Reynolds number is low, the flow is laminar. At least to experimental precision, all of his data collapse onto a single curve. So that's the curve where we are going up to Reynolds number approximately 2000. And this is the laminar regime, and friction factor F goes as inverse of Reynolds number. So this is something we can predict exactly. Around 2000 Reynolds number, there's a sudden and abrupt transition to turbulence, and friction, instead of decreasing with Reynolds number, starts to now increase with Reynolds number. And in this initial region of increase with Reynolds number, again to experimental precision, all of these 6 different curves for 6 different roughnesses, the friction curves, are all collapsed onto a single bundle. But when he cranked up the Reynolds number more, there's something rather interesting that you see. You see a whole constellation of interesting features. So now each of the curve that corresponded to the different roughnesses are separated out. This is the roughest pipe, this is the second roughest pipe, the third roughest, so on and so forth. So I'll focus your attention onto a few key features of this diagram. When we go from this transition regime onto this part where the flow has started to become fully turbulent, the different curves, except for the curve for the highest roughness pipe, all of the other curves go through a maximum. We're going to refer to this maximum as a hump. Post the maximum, we continue to plunge around this straight line, and a straight line in a log-log plot is a power law. And empirically, this power law has been determined, and it's called the Blasius empirical scaling, to where friction scales as Reynolds to the power -1/4. I continue along this power law up to different Reynolds numbers. And basically, as I keep making my pipe smoother, I keep going further and further down the Blasius scaling. And at some point, I separate out from the Blasius scaling and go through this minima. And this minima, we are calling the belly. And finally, when the Reynolds number is very large, we reach an asymptotic state where the friction does not depend on the Reynolds number anymore. But clearly, the friction depends on what the roughness of the pipe is. This friction is higher than friction over here. So if we now take this asymptotic value of the friction and plot it against the roughness, we're going to find another power law in the rough regime, in the rough extreme. And this power law is again an empirical scaling obtained by fitting data. And this is called the Strickler scaling. And this asymptotic value of the friction now does not depend on the Reynolds number, but it depends on the roughness to the power 1/3. So these exponent of Blasius -1/4 and the exponent of Strickler 1/3, these are all empirically determined exponents. I should mention another thing about the Strickler scaling. Those of you who have a background in civil engineering might know this Strickler scaling in another form, which is the Manning formula. The two things are very closely related with each other. Okay, so here are the main key features of how the friction behaves in terms of Reynolds number and roughness. And it's rather interesting that a mundane looking problem like water flowing through a rough pipe can give rise to such an interesting constellation of features. But let's ask a different question. How much of these features do we actually understand? When the flow is laminar, so the Reynolds number is small, the flow is Poiseuille, so we understand this quite well. But from the point of transition to turbulence, why do we have a hump? Why is it that we follow a scaling over here, which is the Blasius scaling? And where does this exponent come from? Why do we have a belly after a Blasius scaling? And why do we have a regime where the friction is independent of Reynolds number, but depends on roughness to the power 1/3? Where does this exponent 1/3 come from? These are things we don't really understand well. And of course, this is a key problem that we would like to understand better. And that's what I'm going to try to explain using some very simple ideas that we have developed. And this is the core of what I'm going to call the spectral link. So for later reference, I'm going to point out one thing. which is that when we're talking about the Blasch's scaling, you would notice that we continue further and further down the scaling as we continue to reduce down the roughness. So effectively, the Blasch's scaling can be taken as an asymptote that corresponds to a smooth pipe. There are subtleties about that, and we can discuss that later. But for the time being, let's take this Blasch's scaling to be an asymptote for the smooth pipe. Likewise, when we go to the other extreme and we come to the Strickler scaling, that's the asymptote for the rough regime. So we have a smooth scaling and we have a rough scaling, and we shall try to understand where this exponents 1/4 and 1/3 comes from, and where do these features hump and the bellies come from. Okay, now to have a contrast or for reference, let me just very briefly outline what the standard approach to predicting, the classical approach to predicting turbulent friction is. So this is, textbook material. This goes back to the classical pioneering work of Ludwig Prandtl and von Karman. They argued that to predict the turbulent friction, we should approach the problem in an indirect way. What do I mean by indirect way? Instead of looking at the turbulent friction, let's look at the mean velocity profile. So this is the wall, and this is the velocity average as a distance from the wall, u of y. So this is our mean velocity profile. And the typical argument is that let us introduce a velocity scale, which we call the friction velocity u tau, which is basically just the shear stress on the wall, the turbulent friction, expressed in the dimensions of velocity. And this, of course, is directly related with the friction factor like this. Now, after introducing this velocity scale, if we go through dimension analysis and similarity analysis, we come to the result, classical result, very well-known result of log law, which states that in a region which is not too close to the wall or too close to the center line, so we are in some intermediate asymptotic region, the velocity, the mean velocity profile goes as logarithm of the distance from the wall. And in this analysis, we have two constants, which we cannot derive from theory. So these are empirical constants at this point. So we have the von Karman constant K, and we have the offset of the log law, capital B. Okay, so once we have this log law, we have an explicit formula that describes the mean velocity profile. And in this explicit formula, we have friction factor hiding in there. As a next step, what we argue is that although we have derived the log law only for an intermediate region of the flow, let us ignore that restriction and integrate the log law across the whole cross-section of the pipe. So from the center line all the way down to the wall. And if we do that, then mass conservation and kinematic constraints that this integral has to be equal to whatever is the flux that's being conveyed by the pipe. So this cross-section area of the pipe multiplied by the mean velocity of the flow. So with this kinematic constraint, and here in the velocity profile u, we are going to input this log law region over here. Performing this integral through, we arrive at this implicit equation for the friction factor. So this is an equation that tells us how the friction factor F and the Reynolds number Re are related with each other. So this is the case for a smooth wall, and these constants A and B are related to the constants kappa and B. Okay, one can also do a very similar analysis for the case of rough wall, and one arrives at a similar looking equation. And using these two fitting parameters, we can then predict how the friction behaves as a function of Reynolds number. And this has been a very, very powerful approach and a very useful approach over the years. But you can already see that the approach is indirect. And also, perhaps more importantly, we can't really say where the exponents of Blasch's and Strickler are coming from analysis like this. Neither can we say where these features like hump and bellies are coming from. So clearly, we would like to understand things better. And that's the motivation for us to approach this problem from a different way. And that different way is going to be the approach of spectral link that I'm going to describe next. But before I get to the spectral link, let me just set out some very elementary ideas about spectrum itself. So I'm going to start with this sketch, this very famous sketch by Da Vinci, where he's showing a jet of water plunging into a pool of water and then rendering the whole pool of water turbulent. Instead of a realistic picture of how a turbulent pool of water looks like, which is a mess of bubbles and who knows what, Da Vinci shows, using a theorist's eye, how we can actually conceptualize the turbulent flow in this pool of water. So what he's showing us is, let us imagine all the mess of the turbulent flow inside the pool of water as an assemblage or a superposition of spinning, whirling flow elements. We can call them eddies, fluctuations, vortices, what you name it. And these eddies are of different sizes. And then when we superpose all these eddies together, we have a turbulent flow. The largest eddies span the scale of the flow, and we have intermediate size eddies all the way down to very, very small eddies. So we have a whole range of scales coming into picture. So that's the kind of a theorist way of imagining a turbulent flow, a superposition of eddies. So this is a sketch that dates back to the late 15th century. And if we fast forward 500 years, we can go to Kolmogorov, who introduced the idea based on ideas, building on ideas by Richardson and Taylor, the notion of an energy cascade. So I just show kind of a cartoon view of what Kolmogorov's notion of an energy, or the framework of an energy cascade is. So we inject energy into the flow, let's say from the mean flow, injecting energy into the turbulent fluctuations. So the mean flow injects energy into the turbulent fluctuations at the largest scales. For a pipe flow, we can take the largest scales of the pipe flow to be something that scales with the radius of the pipe, and the velocity something that scales with the mean flow velocity. So now these eddies are being conveyed energy from the mean flow, but they themselves are unstable. So they split to convey the energy to smaller scale eddies, which in turn are unstable, that split to convey energy to even smaller scale eddies, so on and so forth, till we get a whole range of length scales of eddies superposed onto each other, till the point that the eddies become so small that viscosity can no longer be neglected. Viscous effects become very important, and the energy is dissipated into heat by viscous effects. A key notion in the idea of an energy cascade is, when we look at a statistically stationary state, we are injecting energy at the large length scales at some rate, and that energy is being communicated and passed through the different levels of this cascade and dissipated at the same rate. And that rate we denote as epsilon, which is the turbulent power or the turbulent energy per unit time per unit mass. So epsilon is the conserved quantity across the different levels of this cascade. Okay, with that idea in mind, we can now start to make some rather simple predictions about how the velocity of the eddies of different sizes is related with the size of those different eddies. So if I take some arbitrary eddy in this cascade, and I denote its size by S and its velocity by US, then the kinetic energy per unit mass for this eddy is going to scale as US square. The only time scale we can form out of these two quantities is S over US. So the turbulent power per unit mass, epsilon, which is K over T, is going to scale as US cube over S. So that's the turbulent power, or the epsilon, for this eddy of size S. Now remember, this eddy is just some arbitrary eddy at some level of the cascade, but where it's receiving its energy from ultimately is the largest scale eddy. So epsilon is set by the largest scale eddy. And to get to that, we then note that the epsilon therefore has to be scaling with the large scale eddy velocity, capital V cube, divided by the length scale of the large scale, which we argued would be something that scales with R. So this is a scaling that actually goes back to G.I. Taylor. So if I take this large scale setting of epsilon and I equate it to any arbitrary scale S, then by equating the two, I arrive at this very simple scaling relation that tells us how the velocity of an eddy, US, scales with the size of the eddy, S. And we get a power law, 1 over 3 over here, and we'll see that this 1 over 3 is going to play a role in our analysis. Okay, so this is about eddy's velocity at any level of the cascade. But the same analysis also tells us where this cascade is going to stop down at the smallest scales. And to get to that, we can simply argue that at the small scales, which sometimes are called the viscous length scale or the Kolmogorov scale, and I'm going to denote it by eta, we can simply compute what the local Reynolds number is. And Reynolds number is, of course, a ratio of inertia to viscous effects. And if inertial effects and viscous effects become comparable, we can take that local Reynolds number to be equal to 1, substitute instead of U eta, this expression over here, simplify the algebra, and we arrive at a power law that tells us how the scale, the smallest length scale, the Kolmogorov scale eta, becomes progressively smaller and smaller as Reynolds number increases. There's another power law where eta goes as Reynolds number to the power minus 3/4. So in the analysis I'm going to show next, I'm going to make use of this power law, also of this power law. And another thing that's useful to remember for what I'm going to do is that right from this expression, we can not only predict the velocity of an eddy, but qualitatively we can also see that larger the size of the eddy, larger is the velocity of the eddy. And that's going to become important when we do our analysis. Okay, so these were basically just very basic ideas of Kolmogorov's theory, phenomenological theory of turbulence. And now I want to start introducing the ideas of spectral link, building on the ideas or the background that I've described so far. So if we go back to the problem of turbulent flow inside a rough pipe. Of course, it's a very, very complicated problem to analyze with some very rigorous tools. So we are going to introduce simplifications. And these simplifications are going to be drastic. And the work that I'll describe today is the simplest model that we could construct. So let's see, what are the key simplifications that we introduce? We have a mean flow, which has a complicated profile. And superposed on the mean flow, we have a turbulent fluctuations of all kinds of length scales, which also has its own complications. But the first drastic simplification that we'll introduce is that all of those turbulent fluctuations, all of the dynamics of the turbulent fluctuations, we are going to approximate it as Kolmogorov's energy cascade. So that's how I'm going to describe all of the turbulent fluctuations. Now, the part that we are most interested in is to come to grips with why or how we can predict the turbulent friction between this rough surface and the turbulent flow above. So let us focus on this interface between the rough surface and the turbulent flow above. And let's look at the mean flow across this interface. So if I zoom in at this interface, here is one of those roughnesses, and here's the flow above. We note that because of the geometric sheltering of the roughness, the mean flow is not going to, we're not going to have a mean flow going across, or if it goes across, it's going to be rather small. So how small? We take the extreme. We drastically simplify it and we say, well, there is no mean flow in this region, in this cove region between the roughnesses. So the mean flow in the cove region is 0. As we go above this rough surface, going towards the center line of the pipe, the mean velocity keeps increasing. There's some kind of a complicated profile. But if we focus in the regime of very high Reynolds number, that complicated profile, again, drastic simplification, can be roughly thought of like a plug flow that's moving through. So in other words, I'm binarizing the mean flow. Inside the cove, I'm taking the mean flow to be equal to 0. And outside the cove, in the outer region, I'm taking the whole mean flow to be of single velocity. If I make this simplification, then mass conservation constrains that the value of that velocity has to be exactly equal to the mean velocity of the flow. Thus, what we have is a large momentum, rho times v, where rho is the density of the fluid, in the outer region. And in the cove region, we have 0 momentum. So we have a momentum contrast across this interface where we have the shear stress tau. And this momentum contrast is equal to rho v minus 0, which is rho v. Okay, so that's the momentum contrast in the mean flow. Superposed on this mean flow are turbulent fluctuations. And these turbulent fluctuations ultimately are the entities that affect the turbulent shear stress or the turbulent friction. So let's take one turbulent eddy of size s, whose velocity we denote by us. And we ask, what is the shear stress produced by this turbulent eddy? The physical mechanism here is, and the idea is the same idea as eddy viscosity, which is that these eddies are transferring momentum from this 0 momentum region to this high momentum region. So because of the transfer of momentum, we have shear stress that's produced at the interface. What is the shear stress that's produced by this eddy of velocity us? That's very simple to estimate. It is equal to the momentum contrast, which is rho v, as we argued in the last slide, multiplied by the rate of transfer, which is equal to the velocity of the eddy us. So this eddy of size s is transferring momentum so that the shear stress is rho v times us. Now, the total shear stress at this interface is a superposition of eddies transferring momentum from very, very small eddies to the largest size eddies in the flow. But note that, as we have seen before, the larger the size of the eddy, the larger is going to be the value of US, and therefore larger the contribution to tau. So if we ask of all these different eddies that are affecting this momentum transfer, and therefore that are affecting the turbulent friction, what is the dominant contribution? Which eddy is contributing dominantly to the shear stress? If you ask that question, then geometry tells us the answer, because if we have some very small eddies, its contribution is going to be quite small, but the larger the eddy, the larger the contribution. So therefore, the largest eddy that fits in this cove is going to have the dominant contribution to the shear stress. And this is where the simplicity of using single length scale roughness kicks in. The dominant eddy therefore scales with the size, the roughness size, small r. Eddies that are smaller than this dominant eddy will have a smaller contribution to the flow, to tau, and eddies that are larger than r do not fit in this cove, and therefore only a component of that will contribute to the tau. So the dominant contribution is going to come from S scaling with the size of the roughness r. All right, so now we have all of the basic elements from this very, very simple with the drastic simplifications model, and let's put together all of these different ideas together. So we have this equation for the turbulent shear stress that we derived, and we can now turn it back into friction factor by just non-dimensionalizing it. And so what we find is that the friction factor S is nothing but the velocity of the dominant eddy divided by the mean velocity of the flow. So that's the prediction from this simple model. Let's see how well the prediction works. And to do that, we note that the velocity of an eddy of any size we can describe using Kolmogorov's picture of energy cascade. So I just substitute this back in here, and we find that the friction factor goes as the size of the dominant eddy divided by the radius of the pipe to the power 1/3. And you can already see where I'm going and how I'm going to get the Strickler scaling from here. We've already argued with this equation that when the wall is rough, Reynolds number is very large, the size of the dominant eddy scales with the roughness of the pipe, and therefore we substitute S scales as R, or friction scales as the roughness to the power 1/3, where this 1/3 directly comes from this 1/3 over here, which in turn is tied to the concept of energy cascade. So now we can understand where this empirical exponent in Strickler scaling of 1/3 comes from by connecting it with Kolmogorov's idea of energy cascade. But when we now start to think about the smooth scaling, the Blasch's scaling, we arrive at an absurd result. Because basically, what we are saying is that the smooth pipe is the one that corresponds to roughness going to 0. So therefore, my friction has to go to 0 if we follow ideas like this. That, of course, is not what we see. So something has gone wrong in that reasoning. But if we think about it, while at least in principle, we can make roughness arbitrarily small, S is the size of a physical eddy. And a physical eddy cannot be made arbitrarily small because it's bounded from below by the Kolmogorov length scale. So when we are looking at the smooth limit, we have to look at the smallest size eddies that are realizable in a flow, and those are the Kolmogorov length scale eddies. So the smooth limit corresponds to S scaling as eta, the Kolmogorov length scale, which again, we can use Kolmogorov's theory to get the scaling law for how eta changes with Reynolds number. Take this guy, substitute it here in this equation, this 1/3 and this 3 cancel out, and voila, we get Reynolds number to the power -1/4. So again, this exponent, the Blasch's empirical exponent, now we can derive by connecting it explicitly with Kolmogorov's idea of an energy cascade. So we have derived these two asymptotic limits, the smooth limit of the Blasch's scaling and the rough limit of the Strickler scaling, using these very simple ideas. Now, with these two asymptotes, meaning S scaling as the roughness for high Reynolds number rough pipes, and F scaling as the Kolmogorov length scale eta for smooth pipes, we can also derive the transition between the rough and the smooth scaling because we know the two asymptotes. And just to illustrate how we can go about it, I'm going to take a very simple approach and simply take a linear combination of these two asymptotic limits. We can come up with all kinds of combinations, and essentially the results are quite robust. So I'm just going to show you results for this simple linear combination. And with this linear combination, I substitute it back in this expression over here, and I plot an Ikuratse-like diagram where I plot logarithm of friction against logarithm of Reynolds number for pipes of different roughness. Of course, I'm going to get my asymptotic scalings of Blasius and Strickler exactly. But what I see is that between the two, we have a monotonic transition from Blasius scaling to Strickler scaling. We don't see those very interesting features of bellies or that of the hump. So perhaps our model is way too simple to be able to capture those rather interesting features of bellies and hump. So can we still build on the framework that we have developed so far and try to understand where the bellies and hump come from? So that's what I'm going to try to do next. And to do that, I'm going to slightly shift our perspective and talk about the energy spectrum. So we'll go from real space to Fourier space. And I'm going to denote the turbulent energy spectrum with E of k, where k is the wave number. And the connection with the things that we have described so far can be very simply seen from this transformation over here. If we know the energy spectrum, which basically tells us how the kinetic energy is distributed of eddies of different sizes, we can integrate the energy spectrum to get velocity of eddy of any size s. K is the wave number, which is inversely related to the size of any eddy. Kolmogorov argued that using dimension analysis, that the energy spectrum in the so-called inertial range is only dependent on two variables, epsilon, the turbulent power per unit mass, and the wave number k. With that, dimension analysis tells us that E of k has to scale as k to the power minus 5/3. So this is the famous 5/3 law of turbulence that Kolmogorov derived in 1941. And in place of epsilon, if we substitute the Taylor scaling of v cube over r, and then take this guy and substitute over here, perform the integral, we go back to the exact same thing that we had derived before using real space arguments, because this is basically just the Fourier analog of the same arguments that we have presented before. Okay, now another thing that's useful to think about here is we had derived using the momentum transfer argument that the friction factor scales as the velocity of the dominant eddy divided by the mean velocity of the flow. And the velocity of the dominant eddy is simply square root of this guy over here. So therefore, we can now express the friction factor in terms of this integral transform. So note that in this model, if you give me what the form of the energy spectrum is, we can in fact predict how the friction is going to be. In other words, friction is but a transform of the spectrum. Okay, so why introduce this energy spectrum? What's the benefit that we are going to get from it? Well, one thing is it gives us a very simple visual way to think about what is the missing element in our model. So to illustrate that, here I'm showing some experimental data of energy spectra in rough pipes, plotting in a log-log curve, E of k versus k. And what you see, k is again the wave number, so it's proportional to inverse of the size of an eddy. If we are looking at intermediate size eddies, so intermediate values of k, we see a nice power law with an exponent minus 5/3, just like Kolmogorov had predicted. But if we go to high k, which is small values of small sizes of eddy, dissipative corrections kick in, viscosity kicks in and takes energy away from this inertial transfer of epsilon, and my energy goes down as compared to the power law of k to the power minus 5/3. So we're going to call these corrections to the inertial range correction, to the inertial range as the dissipative correction. Likewise, if I go to large size eddies, this is a power law, and of course we have a finite domain, so I can't have a power law that keeps going forever. So geometrical confinement of the radius of the pipe kicks in, and that again takes energy away from the power law. And these corrections to the inertial range, I'm going to call them energetic corrections. The dissipative correction roughly kick in at a length scale comparable to the Kolmogorov length scale eta, and the energetic correction kick in at a length scale corresponding to radius of the pipe. Okay. So that's the whole structure of the energy spectrum. And in the analysis that I presented so far, we just simply assume it's minus 5/3 throughout. we neglected the dissipative corrections and the energetic correction. So let's take these corrections into account and see how far we can go with these simple ideas. I'll start with the dissipative range correction. So I have the inertial range, and then at a wave number around 1 over eta, we have a dissipative correction coming in. I'm using a well-known equation, a correction for this dissipative range. It's called the power correction, but we can use all kinds of different corrections, some things from Kraichnan and exponential correction, and there are various other forms. The results are quite robust. Anyway, we are trying to see what the qualitative features are and not trying to do any data fitting. So the idea is that we have an inertial range and we have a dissipative correction that kicks in at large wave numbers. And then we go through this same formula, which I'm going to describe as the spectral link, that is the transform between the energy spectrum and the friction factor. So I substitute this in here and then theoretically compute what a Nikuradse-like diagram will look like. So we have the inertial range and the dissipative correction. What do we see? Well, this is what we see. Of course, we'll get the right asymptotic limits by construction. We have the Blashes scaling over here, Strickler scaling over here. But unlike when we were not taking into account the dissipative range correction, we don't have a monotonic transition between the two. Indeed, we start to go through minima and we start to see that the bellies that were so evident and prominent in Nikuradse's data are reproduced over here when we take into account the dissipative range correction. So the bellies are manifestation of the dissipative range of the energy spectrum. Let's now go and try to attack the full problem. By that, I mean, we take the inertial range, we take the dissipative range correction, and also we take the energetic range correction, which is coming from the geometric effect of confinement of the pipe. And if we take this whole region of the spectrum, and then we compute our theoretical values of the friction in a Nikuradse-like diagram, and plot it just like Nikuradse, log of friction against log of Reynolds number, well, this is what we see. We see right from the transition, the point of developing a hump, the fact that for the higher roughnesses, you actually don't have a Strickler regime or a hump. But as the roughness is made smaller, you're going to go through a Strickler regime, a Blashes regime. Then we go through this minima, and finally we arrive at a place where the friction is independent of Reynolds number, but conforms well with the Strickler scaling. In other words, all of the different salient features that we have talked about before in terms of Nikuradse's diagram, with this admittedly very simple model, we can understand, at least to first order, where these different features are coming from. And we can quantitatively predict the power law exponent of the smooth scaling, the Blashes scaling, and the rough scaling, which is the Strickler scaling. So this is something that Gustavo and I have worked on for many years ago, more than 15 years ago now. And that was the start of this area that we've been calling the spectral link sets. And what I'm going to do for the rest of the talk now is to use these ideas that I've described so far, and instead of looking at a classical problem, which was in this case Nikuradse's classical experiments, we're going to go and explore areas for which we actually don't know the answer, and then see how far we can push this very simple reasonings and hopefully gain some new insight into new problems. So that's what I'm going to do next. Okay, so the idea is we are going to generalize the notions that I've described so far. So let's take our spectral link, which is this transform between the energy spectrum and the friction. And we ask, okay, instead of the Kolmogorov picture for the energy spectrum, what if we have some kind of a generalized spectrum where Ek scales as k to the power minus alpha, and I'm going to refer to alpha as the spectral exponent. In the Kolmogorov picture of the energy cascade, alpha is equal to 5 over 3. But for whatever reason, if alpha were different from 5 over 3, what would the kind of analysis that I've described so far, what kind of predictions would we get from that analysis? Well, it's very straightforward to follow the analysis that I've described so far, and then get a generalized Blashes or a generalized scaling for the smooth limit of friction, and a generalized scaling for the rough limit of friction. So in this generalized scaling, friction scales as Reynolds number to the power an exponent that is solely determined by the spectral exponent alpha. When alpha is 5/3, this is the classical Blashes exponent of -1/4. Likewise, for the rough scaling, the generalized Strickler, friction depends solely on roughness to the power an exponent that is determined only by alpha. When alpha is 5/3, this exponent is 1/3, the classical Strickler exponent. But if alpha were different from 5/3, we are going to have new scaling laws for the smooth scaling and the rough scaling. Why should alpha be different from 5/3? Well, there are various ways to go about it. For example, you can have additives introduced in the flow, like polymers, bubbles, sediments, or you can approach by modulating alpha in a different way by controlling geometry. And it's this latter approach of controlling geometry that I'll describe. So the way we go about it is we go from three-dimensional pipe flow into quasi-two-dimensional flows. And a very nice way to realize quasi-two-dimensional flows in an experiment is to use what is called a soap film channel, which I'm schematically showing over here. So the idea is quite simple. You take a bucket and you take some soap, dishwasher detergent, 2% solution mixed in water. And this bucket you place at some height. And from the bottom of the bucket, through a valve, you slowly release the soapy solution. Gravity is going to trickle this solution down into a stream. And with nylon wires, we guide the solution across a triangle-shaped region like this. So at the apex of the triangle, we are feeding the soapy solution. And because of gravity, that solution is going to go down and it's going to be clinging to these nylon wires and therefore will be spreading out into a film. Effectively, this is just a way of blowing a planar bubble, where the job of blowing is done by gravity. And when we reach whichever kind of a width that we would like, then we guide this soapy solution film, the soap film, onto two walls. These are our walls of the channel. And I'm going to first focus on the smooth limit. So I'm going to focus on the smooth wall, and I'll shortly introduce why we are making the other wall rough. Okay, now this film flows through these two walls, these two parallel walls. And at the end of the channel, it comes back with this lower triangle to another bucket. And then we pump it back to the top bucket. And this film can be quite stable. In fact, if you're doing this experiment properly, you can keep the film stable for order of many, many hours. Okay, so that's the very simple setup. And just to get a sense of what kind of dimensions we are talking about, the thickness of the film is of the order of 5 to 10 microns, but the film can be a few centimeters wide and a meter or more tall. So it's really very, very thin compared to how wide and how tall it is. So therefore, it's kind of like a quasi-two-dimensional flow. At the top entrance of this channel, we introduce a series of rods, basically a grid. And if we do that, then as the film flows through this rod, these rods shed eddies, they turn the flow turbulent, and the flow is now decaying 2D turbulence from these rods. And going back to the analysis, theoretical analysis by Kreitman and Batchelor, we know that for a 2D decaying turbulence, what you're going to have is the so-called entropy cascade. The important part for us is that the energy spectra has a spectral exponent equal to 3. And here are some measurements that we have done to indeed verify that our film corresponds to the spectral exponent of 3. Then we use the technique of LDV, laser Doppler velocimetry, to compute the whole velocity profile across the width of the channel. And we can go very, very close to the smooth wall and in fact get inside the viscous layer and calculate the stress, shear stress on the wall precisely. So with that, we can then test what is it that we are going to see from the spectral link. From the spectral link, we would find that the Blashes scaling or the smooth scaling corresponds to RE to the power minus half, not -1/4, but minus half, because alpha is different. And if we take all of our experimental data and we plot it log of friction against log of Reynolds number, for over a decade in Reynolds number, we can see that in fact our data quite nicely conforms with RE to the power minus half, quite distinct from -1/4. Now, one of the charms of this kind of two-dimensional or quasi-two-dimensional experiments is that in the exact same setup, we can actually realize a completely different spectral exponent. That's because 2D turbulent flows allows for two very different kinds of cascades. I showed you entropy cascade, but if in the same exact setup, if we go up and remove the grid and instead put a large rod, then this large rod sheds kind of very large scale vortices, which pick up vortices from this rough wall. And this is the region we have one of the wall rough. And this rough wall is basically acting like a forcing throughout the flow. And then it picks up this turbulence created by the rough wall and spreads it all across the width of the channel. And for a forced 2D turbulence case, we have what is called an inverse energy cascade. And the important part for us is that the spectral exponent is 5/3, just like in a pipe, but instead of a forward cascade, we now have an inverse cascade. But in the framework of the theory, the direction of the cascade does not matter. What matters is the spectral exponent. Then we go through the exact same way to calculate the friction, calculate the Reynolds number, so on and so forth. And of course, with the spectral link, we predict that we are going to get the same Blacher scaling as before. And indeed, when we plot our data now corresponds to the Blacher scaling with -1/4. In other words, with the same exact setup, we can, just by tweaking the entrance of the channel, make the flow conform either to alpha equals 3 or alpha equals 5/3. Everything else is the same. And yet, we can see that there are two completely different families of how the friction behaves with Reynolds number. They correspond to completely different power laws whose exponents a priori we can predict using the idea of a spectral link. So the relationship between friction and Reynolds number, I think these experiments nicely illustrate, is set by the spectral exponent. And note that none of these ideas of the connection with this energy spectrum is there in the classical approach by Prandtl and von Karman. So from that perspective, we must recognize that that approach is incomplete. Okay, let me give one final example, which is, let's go for the full rough pipe. So now we take both walls to be rough. This is a considerably more difficult experiment where, and I can get into the details if people are interested, but we basically go through the same thing, that we put a grid at the top of the channel. It produces entropy cascade, which we can verify by computing the energy spectrum. E of k scales as k to the power -3. And now, instead of using LDV, we use the technique of particle image velocimetry, PIV, and we compute over the length of one or two wavelength of the roughnesses, the shear stress that is produced at the interface between the rough wall and the flow. And here now we actually have to account for the Reynolds stress because that plays the dominant role. And with that, we now can now start to see what the Strickler scaling or the rough scaling is going to look like. So our data in this asymptotic regime, so here is log of friction against log of Reynolds number. Here is the smooth data for reference. We did experiments with channels of various values of roughness, and we see that you get to this asymptotic regime where the roughness is independent of Reynolds number. But of course, the value of this asymptotic regime does depend on what the roughness is. And if we take this asymptotic value and we plot it against the roughness, we get a power law of 1, which is precisely what we would predict for alpha equals 3 using the notion of spectral link. Completely and distinctly different from the exponent 1/3 that we would get for the case of energy cascade or alpha equals 5/3. Okay, so I hope I've been able to give kind of an overview of some of the ideas that we have been working on as kind of a leitmotif of what motivates this kind of an approach would be to think of it in the following way. If you pick a standard textbook on turbulent flows, you would find some chapters that are devoted to macroscopic properties like friction. And here's the Lagrange diagram. And disjoint separate chapters devoted to the spectral properties like the energy spectrum of the field. And what we are basically saying is that these two are in fact intimately tied to each other. They're linked to each other. And that link in this simple model that I've described is what we are calling the spectral link. If you know the spectrum, we can predict how the friction is going to behave. And from a conceptual point of view, we know a lot more about the spectrum than we know about the friction. So therefore, would be the kind of motivation to pursue an approach like this. Okay, So let me summarize what I've described so far. I started with the classical results of Nikodaz's experiment, and we exactly derived where this exponent 1/4 and 1/3 comes from. And we also were able to get these bellies and the hump. So the different qualitative features in Nikodaz's diagram. So these were things that were known in terms of empirical data that existed, and we were able to theoretically understand and describe where these features are coming from. Then from the known, we jumped into unknown, and we started to explore completely new frictional scaling laws by exploring two-dimensional flows, by basically modulating the energy spectrum. And by modulating the energy spectrum on a smooth wall flow, we derived two distinct power laws for the energies, for the frictional scaling, and the exponent of the power law is purely set by the spectral exponent that governs the flow. And finally, we looked at rough flow and entropy cascade in a rough flow, and we found a new power law for the Strickler regime. So if I have to summarize all of these different things in just a single sentence, what I would say is that macroscopic properties of turbulent flows, like the turbulent friction, are all very intimately tied to the spectrum. That's the core idea of the spectrum. And if the ideas that I've described so far are of any interest, we have published a few papers where we have explored many different aspects of the spectral link, and I'll leave the reference list here in case anybody's interested with that. Okay, I thank you very much for your kind attention, and if you have any questions, I'll be happy to try to answer them.
Yeah, thank you, Pinaki, for a very interesting talk. So we have some time to ask a question. So feel free to unmute yourself or just put your comment on the chat. Let me ask some questions. So I guess you use some fitting of a spectrum to create some beta model. And I guess the spectrum is still depending on Reynolds number. So how did you do that fitting?
Sure. So let's go back to part over here. So the Reynolds number dependence comes in two ways. We have the very base model, which is, let's go back here. The very base model of the energy spectrum is the Kolmogorov model, which is epsilon 2/3, k minus 5/3. And there's a constant in front, the Kolmogorov constant, but for everything we are doing, that's just a scaling factor. So it has no effect on any of the results that we're describing so far. Now, to your question of where the Reynolds number comes in, note that this epsilon goes with V cube over R. So if we are looking at constant viscosity fluids, then when we are changing the Reynolds number, epsilon is going to change also. And because epsilon is going to change, and in fact, that becomes perhaps even clearer when we look at the Kolmogorov length scale. The Kolmogorov length scale is going to keep becoming smaller and smaller as the Reynolds number is going to increase. So in the energy spectra that we are using, sorry, I'm skipping through many slides over here. This is the form of the energy spectrum. And we have the epsilon that basically sets the amplitude of the energy spectrum that's changing with Reynolds number. We also have this dissipative range that's kicking in at a length scale eta, which changes with Reynolds number. So these are the two places where Reynolds number changes are coming in. The large length, the energetic correction is independent of Reynolds number because that's just a geometric quantity. It only depends on the radius of the pipe.
I see. Okay, so maybe, yeah. So I guess this is the data taken from a pipe.
Yes.
So, okay, I see. Now I understand. Any question? I have another one. So basically the shear stress is the slope of the profile. So even when the wall is smooth, if you are a bit away from the wall, you have some typical size of the eddy. So I guess you can say something about the mean flow, even when your profile is not very close to the wall.
Mhm.
Or am I right? Or
So I couldn't follow the question. Could you please?
okay. Yeah. So probably, as far as I understand, this is the way to find the slope from the spectrum. So you found the slope at the wall, but I guess the position of your concern is not necessarily at wall. So maybe you can find it.
I see the question. Okay. Yeah. So you're right. So I think I should maybe. So kind of like the question is, how close to the wall should we measure the spectrum, and how close are we talking about? Because of course, if we go very, very close to the wall, then we are going to get inside the viscous layer, and there is effectively no turbulence there. We're going to have laminar flow over there. So clearly, we have to be above the viscous layer. But here is something that I should mention, and this is what I was referring to in terms of drastic simplification. So what we in reality have is a rather complicated profile of the mean velocity, for one. So if I go, let's say, from here, going further up, I'm going to have the mean velocity that increases, perhaps going through some kind of a logarithmic region, wake region, so on and so forth. Quite a complicated profile. But to make progress, we just binarize the whole mean velocity profile and said, inside this region, you have very little momentum going through. So we're just making it 0. And then we have a jump of velocity outside this region, where all of the bulk velocity is just single velocity. So the complicated profile, we just make it into a step function. And in that idealization, we would then measure the spectrum right at the interface. But that's not the real flow. That's an idealization. Now, what that corresponds to in a real flow is a very difficult question to answer. So what we have done so far largely is we have focused on flows where the spectral behavior is uniform across the whole length of the channel. But we have also done some experiments. I'll just briefly show you, where in fact you can start to do non-uniform flows. So here's a soap film, and we start to disturb, instead of putting our grid perpendicular to the flow, we put our grid parallel to a wall. And what you can see if you start to do that, these are just accidents that happen in a lab, and then you start to explore them. You see that just these are fringes. So they tell you, for example, how the thickness is fluctuating or how the velocity is fluctuating. If you put this grid perpendicular to the flow, the turbulence is very uniform across. But if you put the fringe parallel to the flow, the turbulence is quite different next to where the disturbance is compared to further away. More important, if you start to measure the energy spectra, you would see that the energy spectra, in fact, switches. Close to the wall, it's -3. Away from the wall, it's 5/3. And if you measure the friction, it in fact corresponds to the spectra that's measured close to the wall. Now, is there a precise exact location where we can take the spectra and then go forward? I think that would be a very interesting question to probe. But at the level that I've described the analysis, we don't have a precise answer to that. All we can really say is that in this level of extreme simplification, it is at the interface. But in a real flow, it may be you have to do some kind of an averaging to get the spectrum instead of perhaps just measuring at one point. But whichever way you go about it, it's going to be somewhere close to the wall, but not in the viscous layer.
I see. Yeah, that makes sense. Yeah, and I found that this experiment is very nice, very, how to say, very nice way to see this spectrum. Yeah. Any other question? So
I just have a quick question, which is just picking up on a comment you made, which was that the two-sided rough pipe experiments were much more difficult. And I just wondered why was that?
Okay, so it's basically a technical point, but let me try to explain how. So let's see how actually we measure the friction. So to do it with the smooth pipe, with the smooth channel, so we can have one wall smooth, or in fact both walls smooth, and we have done for both, the results are the same if we just focus on the smooth side. What we do is we shine LDV laser beams at different points across the width of the pipe. So this LDV is on a translation stage, and you just measure the velocity time series here, 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 so on and so forth. And you can measure the whole velocity profile across the whole width of the channel. And then if it's a 2-component LDV, you can also measure the Reynolds stress profile. And what you would find very close to the wall, and in fact, because it's a quasi 2D flow, you can really, really go close to the wall. I'm talking of the order of 10 microns. So you can find that there's in fact going to be a region where the Reynolds stress is 0 or very, very small, and the whole flow is dominated by viscous stress. So that's the viscous sublayer region, so to speak. And because we have many data points over there, we can just take the slope of the velocity profile and compute what the friction is just by looking at the viscous stress. So using LDV profile across the width of the channel, you can get the data rather straightforward. And these LDV experiments are fairly straightforward to do, and you can do it quite quickly. Now let's consider the rough one. When we now talk about the rough flow, we were interested in the interface between the rough wall and the flow here. The no slip boundary condition is going to be pertaining to region over here. So therefore, right now, my viscous sublayer is going to be coating this region over here. And the interface that I'm measuring, where I'm measuring the shear stress, is going to be dominated by turbulent flow. So I'll have to, first of all, make sure that in fact, the viscous stress doesn't play a big role. I have to get a good profile of the Reynolds stress all the way across. Further, if I want to do these measurements carefully, the Reynolds stress over here is going to be different than over here. It's going to be different than over here, and so forth. In other words, I'm going to have an X or a streamwise profile of the Reynolds stress. Is going to have some shape that looks like this, and then take an average of the whole thing. In other words, I can't just have some single point measurements with an LDV, or if I want to do that, I would really have to put a very finely spaced grid. So we switch technique and use the technique of PIV, where we can get velocity fields. Now, LDV, you're dealing with a beam, but PIV, you're dealing with a laser sheet. And reflections and all kinds of other complications of introducing the sheet with respect to a beam are actually significantly harder. And that's the technical reason why doing the experiments for the rough channel is harder than doing it from the smooth channel. It took us many years to kind of get this working right.
Yeah. Oh no, that's so interesting. Thank you for answering my question.
Yeah, any other questions? Yeah, go ahead, Rahul.
Hi, Professor Chakraborty. Thanks for the talk. I'm Rahul from the University of Melbourne. And just following up the question from Dr. Teguchi. So the spectrum that you have reported, at what height did you take measurements for these?
Okay, so for example, let's see, well, let's start with this. So what we did, and we had to make sure that we have flows with uniform spectrum. So we started with effectively right outside the viscous layer and all the way to center line. The dark lines that you're seeing over here are the spectra that are measured about 1 millimeter away from the wall. And the light lines that you're seeing here are the spectra that are measured at the center line. So we wanted to make sure that all across the width of the pipe, of the channel in this case, you have the same spectral exponent, which in this case is -3. And incidentally, the the dotted versus the solid curve correspond to the UU spectra and the VV spectra. So we wanted to make sure that in any case, we are always talking about a single spectral exponent that characterizes the whole flow. But as I mentioned, we can in fact also look at cases where the spectral exponent is changing across the width of the flow. And in that case, it looks like the spectral exponent that is close to the wall is the one that determines. But if your spectral exponent is continuously changing, then we as yet don't have an answer as to at what distance from the wall we have to measure the spectrum and which spectral exponent at that distance really sets the friction scale.
Okay. So for example, in this experiment where you have a smooth wall on the left and the rough wall on the right, you're saying if you want to predict the drag for the smooth wall, then go close to the smooth wall, and then instead of the rough wall, go close to the rough wall then.
Precisely, yes.
Okay. Thank you.
Sure. But how close is something that, it's still iffy.
But you emphasize it should be outside the viscous.
Absolutely, yes.
Thank you.
Yeah, so this model is really simple and powerful. I guess you consider some more extension, I guess.
Yes, in fact, if I can just give a plug-in. So in this 2010 paper, we actually looked at, and this is related with many of the questions that we've been asked, what is happening when you're actually going at different distances away from the wall? So what's happening is, of course, the mean velocity profile, the mean velocity itself is changing, you have a profile. But the form of the energy spectrum is also changing when you're going at different distances from the wall. For one, the dissipated epsilon also has a profile, just like mean velocity has a profile. So therefore, the energy spectrum is also a function of y. So it's not just E of k, but E of k and y. So for a smooth wall flow, we were able to derive using very similar ideas that I've described so far, but now explicitly consider different distances from the wall and not only derive the frictional scaling, but which meaning how friction scales with Reynolds number, but get the whole mean velocity profile from the viscous sublayer to the buffer layer to the log layer to the wake. And in this case, relate these different parts of the mean velocity profile to different parts of the spectrum. In fact, we are able to show that the inertial range of the spectrum sets the log layer of the mean velocity profile. The dissipative range of the spectrum sets the buffer layer of the mean velocity profile. And the energetic range of the spectrum sets the wake region of the mean velocity profile. So, but we were so far only able to do that for smooth wall flows. It would be nice to try it out for rough wall flows, which I hope to try someday.
Yeah, very interesting. So this is a practically important problem, I think. Yeah. Any other question? Yeah. So if not, let's thank for the speaker again.
Thank you very much. Thanks very much for attending the talk.
Yeah, thank you very much for a very interesting talk.
And thanks for inviting me again.